these models. So we're going to have a couple different models here. And one thing to know about models are not a perfect description of reality. Models are our attempt to describe what we find in nature, but they are not nature itself. And because of this, there will be some limitations to the models. Models describe some aspects of what we find in nature, but they don't necessarily describe all aspects. So we have multiple models to address the different aspects that we find in nature. We're going to start off with a type of localized electron bonding model. This just means that the electrons are on the atoms and not shared throughout the whole molecule. Electrons are going to be either in bonding pairs between the atoms or in lone pairs on one atom. And we're going to start off using Lewis structures to describe where the electrons are, whether we have bonding pairs or lone pairs. Then we're going to use valence shell electron pair repulsion to describe the geometry of the molecule. Then we're going to go into hybrid orbitals to describe the types of atomic orbitals that are holding these electrons. In geometry, we have two types of geometry. We're going to have electron geometry. This is how the electron pairs are structured around the atom. And generally, we're looking at the central atom of a simple molecule that only has one central atom. But some of these electron pairs are going to be lone pairs. Lone pairs are not sticking out of the atom. It's only the bonding pairs that are holding a atom that end up being visible in the molecular geometry. So the molecular geometry is the structure of the atoms in the molecule. The lone pairs that are in the electron geometry, they hold the shape that will structure the molecular geometry. So we're going to start off determining the electron geometry of the molecules, then use that to help us to determine the molecular geometry of the molecules. The valence shell electron pair repulsion model gives us the geometries of our molecules. It's saying that areas of electron density or electron domains, these are characterized by electrons and bonds, whether they are single, double, or triple bonds, that's going to be one area of electron density, and non-bonding electron pairs, lone pairs of electrons. These electrons all have the same electrical charge, which means that they are repulsive to each other. So these areas try to get as far apart as possible from each other. And using this simple concept, we are able to predict the geometries of our molecules. So we're going to count double bonds, triple bonds, the same as we do a single bond. So they're all one area of electron density, one electron domain. When we have resonant structures, resonant Lewis dot structures, any one of them is useful to predict the molecular structure. They should all give the same molecular structure. If we have two areas of electron density around a central atom, these will get as far apart as possible from each other, which means they'll be on the opposite sides of the atom. So we'll end up with a linear structure with a bond angle of 180 degrees. If we have a complete octet on the central atom, this means that we will be having either two double bonds or a single bond and a triple bond. If we have three areas of electron density around a central atom, to get as far apart as possible, they end up forming a triangle in a plane. We call this trigonal planar geometry. So since it's in a plane, we can figure out the bond angles. It's 1/3 of a circle, which means the bond angle is 120 degrees. If we have a octet-obeying structure, that means that we're going to end up with a double bond and 2 single bonds on this. So these images are just different ways of representing the information. So this one down here is the Lewis dot structure. The center one here, we're using A for the central atom and X for attached atoms. And then this is just showing the 3 atoms and using a ball and stick model. So we have different models of different ways of representing this. The ball and stick model is not representative of the physical structure of the atom. Outside that, we're showing the 4 atoms and their relation to each other. Another one would be the space filling model, such as in the carbon dioxide model here. And this is a better representation of the actual structure. The atoms overlap each other when they form a chemical bond. So each atom is roughly spherical and they overlap each other when they form a bond. And ball and stick allows us to just see these individual atoms a little bit more clearly. If we have 3 areas of electron density, what we just said, trigonal planar electron geometry, but one of those areas is a lone pair and 2 of the areas are atoms. So we have 3 areas. So the 3 areas would be trigonal planar electron geometry, bond angle of 120 degrees. The lone pair, though, since that pair of electrons is not being shared or pulled toward another atom, the lone pair actually takes up a little bit more space. It doesn't literally stick out of the molecule as this diagram shows, or this one over here, but it's in that central atom holding the shape of that trigonal planar electron geometry. But we're going to have an electron pair. So in this structure here, we're going to use E to represent electron pair, the lone pair. So we have that trigonal planar shape, but we're only looking at the pink and 2 white here for the actual molecular structure. So we have 3 atoms. They are definitely not linear, so they are bent molecular geometry. So we have a bent molecular geometry. The lone pair is more repulsive than a bonding pair. So this bond angle on the bottom shrinks a little bit. So it'll be a little bit less than 120 degrees. Whereas the trigonal planar electron geometry would be 120 all the way around. The bent molecular geometry is going to be a little bit less than 120 degrees. If we have 4 areas of electron density, so 4 atoms attached to a octet-obeying central atom, we're going to end up with a structure like this. So we had the trigonal shape from the trigonal planar. We add an atom that the 3 trigonal atoms are pushed down, so they're no longer planar with the central atom. We end up forming, if we fill in the sides here, we form a 4-sided structure. All sides are identical, so that would be a tetragon. Well, we're going to call this a tetrahedral geometry. So if we have a the bond angle of this structure is going to be 109.5 degrees. If we have an octet-obeying structure, that means we're going to have 4 single bonds and no lone pairs on that central atom. If in that tetrahedral electron geometry we have now a lone pair in addition to 3 attached atoms, so lone pair, 3 attached atoms, well, we're chopping off top of the tetrahedral structure. So the sides are no longer coming up to the top of this lone pair here. They're just going to come up to the nitrogen here. So we're going to have a three-sided structure. It's no longer four equal sides. It's going to be three equal sides and then a base. So it's a three-sided structure with a base. The central atom is higher than all the attached atoms. So it has a pyramidal structure. So we're going to call this trigonal pyramidal. And again, we just have a couple different ways of representing, from the Lewis-Dot structure, letter structure, lone pair representation. So we have a trigonal pyramidal, trigonal pyramid, trigonal pyramidal molecular geometry. This is only a molecular geometry. Whenever we have a lone pair on the central atom, the molecular geometry is going to be different from the electron geometry. So the trigonal pyramidal molecular geometry comes from the tetrahedral electron geometry. It's not written down here. But the bond angle, because that lone pair is repulsive, the bond angle is going to make the bond angle less than the 109.5 from the tetrahedral. For ammonia, it's specifically 107 degrees, but it's definitely going to be less than the 109.5 degrees from the tetrahedral. If we start off with that tetrahedral electron geometry, so we still have our 4 Aries electron density, 2 of them are lone pairs, and 2 of them are atoms. So the lone pairs truly don't stick out the way that these representations give it, but they're in that central atom holding the shape. So the tetrahedral starts off with 109.5 bond angle. The lone pairs are more repulsive, so they're going to shrink it. So it's going to be less than 109 degrees. For water specifically, it's 104.5 degrees. So obviously it's not a linear structure with our 3 atoms, so we have another bent molecular geometry. This bent molecular geometry has a different bond angle than the one that comes from the trigonal planar electron geometry. So again, bent is a molecular geometry only. It comes from a tetrahedral electron geometry. So those were the ones that obey the octet rule. Now we're looking at the ones where we can exceed the octet rule. To exceed the octet rule, we're going to need more orbitals. That means we need d orbitals. D orbitals show up on period 3. So that means the central atom has to be a period 3 element or higher in period, so period 4, period 5. So with period 3 or higher elements, we can access the d orbitals and have bonds or Aries electron density that will be more than 8 electrons. So going up to 5 Aries electron density. 5 Aries electron density. If we brought in an atom from the base of the tetrahedral, it would flatten that 3 back out into a trigonal planar structure with an atom on top and an atom on bottom. So we have 5 atoms. These atoms are no longer identical like on the previous ones. They have different positions. So 2 of the atoms are going to be axial atoms, and 3 of the atoms are equatorial atoms. So we're going to have a couple different bond angles here. So an axial atom has a 90-degree bond angle with an equatorial atom. An equatorial atom has a 120-degree bond angle with another equatorial atom. An axial atom has a 180-degree bond angle with the other axial atom. So this geometry is called the trigonal bipyramidal electron geometry, trigonal bipyramidal electron or molecular geometry. So we have our 3 bond angles, 90 degrees, 120 degrees, 180 degrees.